Welcome to this appendix to the last lecture. The idea was to have a short one. This didn't turn out. This is a super interesting topic on the complex numbers and geometry on them. And it turns out to be very complicated in didactics. And it's a little surprising because the principal idea is very simple, but it turns out that it's super complex. And I think it's important for architects to get an idea of that. So to do these things, you need version 1.13, and you need a little patience, because to get these simple things, you need a kind of meditation, repetition, and so on, if you get the proper level of abstraction and appreciate that. So complex numbers are a strange species. They drive our world today. All quantum physics, for example, is in space-time is with complex numbers. And it's also important that complex numbers have the same nature like all numbers. So, and we got a little lazy with understanding that, because we simply and pragmatically use addition, multiplication, the power of things, just to do something. So it's 1 plus 3 is 5, and then we are happy. We don't think what all this stuff is about. So it's always, numbers are always a strange combination between space and time, projections, crisscross, and all these numbers are that. And now with complex numbers, somehow, because they are so strange to us and we are not educated in them, maybe we get a better understanding what natural numbers or the rational numbers or the real numbers are, what their nature is. So therefore I think it's worth to have an eye and be a little patient and try to understand what they are about. So, especially, you cannot see numbers. It's very interesting. You only see and count the traces of numbers. For example, with Latour and so on, we have these discussions, which is, you have to admit, strange and familiar, because you can see a number, but intuitive. So you only can see 3 cows, and they say 1, 2, 3, so the numbers 1, 2, 3. And these are the traces of the numbers, but the numbers you can see. It's interesting. Therefore, all ways how to illustrate or make it intuitive in a visual way what numbers are, how number systems work, or all these complex numbers, they are a kind of dead leg. So this looks interesting, this looks convincing, but it's rhetoric. So I don't think you get numbers with visualization. It's not a visual thing. So you have to trust the words, the conceptions, the principal mathematical concepts, and you have to put that as a skeleton to climb up in abstraction and get better understanding. It's not a visual thing. It's explicitly not. So, as you might know, complex numbers do have 2 parts. Always written like this: 2 times 1 plus 3 times I. So this is a real part, which represents a position on the projection plane in space, I would say, and it's about scaling at length. So it's a linear thing. And the imaginary part here, characterized by this axis, I, is, I say, with time, and it's about a position on a circle in time, and it's about angles and direction, so it's circular. So we have a linear part and we have a circular part. So the axis of the imaginary part is I, with the definition I square equals -1, which makes it circular. I can't explain it here. And the linear part is characterized by 1, which is the straight thing we always know from Cartesian space and we are used to. So this is how it is constituted. It's important for architects, I think, because I think in antiquity, in Renaissance and today, the imaginary part plays with floors and ceilings. It's a vertical, and it's a rotation around the vertical, and the walls and the facade are with the real part. So this is the geometric part. This is what we are discussing this semester, and I want to try to push this idea. So therefore, I think architecture or the scenography is directly play around the nature of numbers and implementation of that, giving space in time, generous space in time. So therefore, there is a nice explanation of what complex numbers are, especially with the quaternions, which is the principal tool how to do 3D modeling. You have visual and explorer video. You can, so it's very well done, super popular, especially these STEREOGRPAHIC projects and 1, 2, and 3-dimensional. It's very interesting, but I think it's not the key of it, as I explained before. So be careful, look it up. It's interesting, but be careful. So now go to the principles. There's addition of complex numbers. It's done like this. So you have the real part, the imaginary part, so just add the real parts, add the imaginary parts, and you have the addition. The multiplication is a little more complicated. So you have the real part and the imaginary part, real, imaginary, multiplication. Then you go real, 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 imaginary, imaginary, real, imaginary, imaginary. It's here. So then you go with the imaginary. I square is -1, you know that. And then you select I from these. This is -1, so this you can put it on the real part. This got real, and this is the imaginary part. That's a multiplication. In Mathematica, it looks like that. So that's arithmetic. You can look it up in Mathematica here. There's a lot of functions around complex numbers. Now go on visualization. So addition and translation with real numbers along a line. So now we have, so this is an addition, which means you keep the absolute distance on a line. That's a linear addition. So this is in Cartesian space an addition on a one-dimensional space. This is a multiplication. A multiplication keeps proportion. It's not the distance, it's a proportion which is kept. It's multiplication. So it's so if you go to do the 2-dimension, this is addition. So which means you have a certain point and you add another point, or now here we have multiple points and we add this point. So which means I can translate this down. This is proper. So this is architects who need. Translation in Cartesian space. So the integrity of this object is intact. That's it. But if we go to multiplication in Cartesian space, look at this. If we have multiplication of 2 numbers here, simple to one, this by this by this, done. Then we get this, we lose the integrity of the object. Look, everything gets distorted. So we can't rotate the object. So we lose, with multiplication in Cartesian space, we lose integrity of the object. That's our problem. So The problem with lines is that they have, so with lines or Cartesian space is that they have no clue about the interplay of things in space. They just cut space and they have the elements and the elements are located and they are disconnected. This is what Cartesian space is doing, cutting space. But things in space, the things in space, they contain a circular harmonics of its parts. So they are connected, they play, and so on. And this is what complex numbers can do. They can keep an understanding of the harmonics of space, because they do have a linear and a circular component, the real and the imaginary part. They do not cut space, they understand space in a holistic way. They don't forget about the connection of things. They don't cut it. This is what multiplication with complex numbers does. It keeps the harmonics of space or the interplay of parts in an element intact. And therefore, you can rotate and scale and keep the object intact, the integrity of that object intact. So therefore, as architects, needing rotations and translation in real numbers by Cartesian space is proper, and rotation in complex space is taken as a multiplication in complex space. That's important, and we can't use this. And we are not happy with operations available in Cartesian space, because we're losing our integrity as soon as we try to turn things and not keep it with translations. Good. Now, this is how it works. There's a video. Step 1, the complex number 1.5 as a triangle in reference to a unit circle. So there's a unit circle and this is a triangle. This is a number and we have this triangle. If we want to multiply, there's another complex number, it's this. And we draw it again with this triangle. So to do the multiplication, we first have a rotation in time. That's this step. So we take the red one and turn it to the hypotenuse of the blue one. That's the rotational part. This corresponds to I conceptually. And then we scale it. This corresponds to the real part. Towards this point, we scale it up to here. And then we reach this point here in complex plane. That's a multiplication. That's a combination of rotation and translation. And by that, integrity keeps intact. So, then it's very important, it's this part here. Be aware that the multiplication rules of complex numbers are following a combinatoric pattern of mutual multiplications. This means that the real part is not, so if you go here, the real part, and this is the imaginary part, it looks like Cartesian for the visualization, but I told you, you can't see it. So what you can see is, it's not the length and space of the complex numbers, but it's a perspective projection into space. And the imaginary part is not the angle in time of the complex numbers, but it's perspective projection into space. So we have a certain projection of a principal idea, and it looks like this Cartesian, but it is not like this. It's very important to keep in mind. So now, complex multiplication and graphics go into a technical detail. So the conventional way of 2D rotation with transformation matrices. So this is how we, for example, Mathematica is offering it as a standard way. So we have an origin and we have a grid, for example, here. This is a function I provided. So we take a point 1 and a point 2. We create a rotation. This is a vector angle between point 1, this is the source, and this is P2 is a screen, and then the screen, and then the length of the screen for scaling. So this is how we do it normally. So we have a strange number here. If you put it to computable numbers, it looks like this. But then we have a pragmatic cut, and we go into rounding errors. So this is a symbolic representation, and this is precise. So all these, if you're at square root, it's always an indicator that you're in circular, so you're in time. So it keeps on a symbolic level these numbers in time. So then, as we discussed before, and this is rotation, transformation of the rotation, and then we have a scaling transformation of our scaling. So we say first scale, dot product, then rotate. This is our transformation function. It looks like this. And our grid 2 is just the graphic transformation to the grid, which is here. We see it by this transformation, which is scaling and rotation, from this point to this point. So, and this is the rendering. So we have the grid with a certain thickness. Grid 1, there's the original one. This is the rotated one. Then we make a point at the origin, and we make a red point points at P1, P2. These are the 2 points, and an arrow from here to here to illustrate what's going on. And here you see the result. So grid 1, it's in the background. You have the point 1, point 2 is here, and this transformation function magically turns and scales the whole thing, so that around this origin, this thing is rotated and stretched to this point, and with it the whole world. So for me, it's very pragmatic to do so. So this is how always this stuff is explained in a pragmatic way. So if you simply say you need a graphic transformation, you need a rotation, then you need a scaling, you need a translation, and make the dot products, and you're done. You can operate on that, and this works. It's good. But I never understood why. And I still don't really get what matrices are. So, and what you learn always is how to do it, this pragmatic way. And this leads you away from what's going on there. So maybe now with the complex number, it's a little more simpler. It's a good entry point to get an understanding what the hell numbers are, what multiplication is, what an addition is, and so on and so on, how this interplay works. So this magically works. Look at the complex numbers. It's the same thing. We have it here. So the point 1, point 2, these are the coordinates. I wrote deliver a function in this new version, MTP to complex plane, so that these 2 points get their complex counterparts. So this means -1, 3 is -1, 3i, and the same here. So this is simple. So the rotation is just a multiplication of these 2 complex numbers, duck, duck. That's it. And then you get it back to, let's say, inverse function to this, get it back to the coordinates. So then we have it. That's it, astonishingly. So if you make that with the whole graphic, for example, here this setup, as we did it with the conventional one, there's a code, a grid, a red dot at 1.0, there's the graphics of the graph, there's rendering of the graphic. Now this rotation function simply takes all the coordinates here, all the points here, and makes this multiplication in complex plane with this point. So all points in code are multiplied with P1 in complex plane and then went back. If I do that, code, this is this one and this one, we are here. And you see this point 10 is here on, it's now 10 in this world, in this consistent world, and it's 10 in this consistent world, or different world, and it's 1.52 in the original world. So the interesting thing is just a multiplication. And I want to understand why it is working like that. So this is an interactive version, you'll get an idea. So this keeps the integrity of things. And you can do it with any kind of form. So if you want to do that with just the rotation, this is the length of a complex number, or if we have this kind of notation as a list, it's the same. If you want the angle of a complex number, and this is just the angle, so it's a projection to the unit circle, and or do it this, which means my point here, if I take that, this one, I can project it to the circle, and then I have just the direction, because the length is 1, so I don't scale. If I do that with my graphics, then it's rotating. And the implementation, if you look it up here, it's just, this is P2, this is the dynamic part, so this is my mouse, it's P2, and I put in here normalize. If I take it out, then I can scale. If I put this in, just normalize, which is this function here, then I only take the direction and have the scaling to 1, keep the scaling to 1, then we are here. Good. You can keep this off, huh? Now you can make it normalize here. P2. Another random one. Good. So that's this story. Okay, this now is on stereographic projection. And this is how space is memorized in time. So this is what time gets from space. So the first protagonist is time. So this is the mechanics of time. So this is this circle. It's on the complex, so-called complex plane. It's the eye. It's the imaginary part is in the vertical, and the rational part is in the horizontal. Just to give you an idea about the mechanics of these numbers, or this in our case about the complex numbers. So this is the time, which is the chronological part of this complex number. So remember, you cannot see, but you can hear and show time, in time. And you cannot hear, but you can see and talk in space. So it's crisscross, and it's sensual and actual, sensual and actual, and this is crisscross. It's very important. Therefore, you cannot see this circle because it's of time and not in space. What you can see is this diagram. Then it's called not a model, but a diagram. And because this diagram is shown in time, so in time you can show in time. So, and then project it to space. Where you can see it. Good. Where you can see it. So it's shown in time and then projected to space to be able to see it. This is a complicated setup and you never should forget that. That's a problem with the rhetoric of the visual and the intuition. The visual intuition is that you simply make this shortcut and say it doesn't matter. So what you also see is there are partitions of this circle, of this unit circle in complex number space. And these partitions are not xy coordinates and points in Cartesian space. These points are projections. These points here are projections of positions of these positions, and you have to read the x, the y as a direction in time, and the length, so the I as a direction, so this is here, it's a direction in time, and the length here, it's the length in space. So therefore, if we are like this, I is read as 1, so 1 is directed as 1 on 0 degree in complex space, which is a length of 1 and 0 in direction and no direction. So I is read as 1 on the vertical axis or 90 degrees with a length of 0, so it's no length on the real part, but a direction of I. Minus 1, so on the horizontal axis 180 degrees, minus 1 on the horizontal axis with a length of minus 1 and no direction. Minus I here is minus 1 on the vertical axis or minus 90 degree with a length of 0, so it's no length, and the direction of minus I. So it's very important to remember that this is not two lengths. It's always length and direction. So you also can move your position in time, which turns the whole world of the unit circle like the firmament is turning over time. I don't know if you want to. Like firmament is turning over time. This notation is not changing the interplay or the harmonics of the parts in time. That's very important. So they are not changing. They are absolute and constant. The mutual angles of the partition stays always the same. That's important. And to add a rotation, the complex numbers on the unit circle are simply multiplied. So, for example, if you are at the position 1, which is an x, and you multiply it with I, which is 90 degrees, then it's I. So it's real, imaginary, and you are here. So now, if you multiply it with another I, This is -1, it goes here. If you multiply with another I, it's going down, it's turning another 90 degrees. And if you do it again, it's at the origin again, so it's turning, making the circle. Or better, powers of I goes in circles. 1, I, -1, -I1, and so on. There is nice YouTube here. I think we have it here. Ethernet, I gave this link. So it's the same what I reproduced with Mathematica. Good. Or we have it here.
Right now, we just want to describe complex number z, where multiplying by z has the effect of a pure rotation, so he only needs to understand the unit circle. For example, when we take the number I and multiply it by any other complex number w.
Go there, you can have another perspective to it, which I warn you, it's just the visual and tries to use the intuition to get an understanding. So, now, just the technical setup. If you want to rotate, a technical challenge, if you want to rotate, for example, 45 degrees with 30 degrees. So then you have to get the points on the unit circle. So on this circle, you have to get the 45 degrees. It's simple. It's 1, 1 here, and then project it here, make it a length 1, and you have it here. With 30 degrees, complicated. You can't find a grid point to make a 30 degree. It's irrational. Only with rational angles you can do that. Very few of them. So therefore, luckily, we have these trigonometric functions, which are numbers and angles, which provides you the consistent arithmetics on the circle. So therefore, we can say cosine of 30 degrees, sine of 30 degrees, and we have the point on the unit circle at the angle of 30 degrees. So this unit circle 45, unit circle 30. So these are these two numbers. Then the complex conversion are here. There's a complex number on the unit circle in complex plane, and that's the 30 degree on complex plane. So then simply multiply these two complex numbers and you get this, this expression. And these square roots always indicate that you're on circle and then are irrational number planes, so not in the visual realm. That's what square roots are doing. So translate them back to the rational Cartesian place. So we have x and y coordinates, and show how it is done. So we see the points. Points here. These are the points. You have 0, 0 in black. 0, 0. That's this one. Then you have U30 and U45. Then you have red point, U75, it's here. So therefore, 30 degrees, 45 degrees, 45 plus 30 degrees is here. So it's this simple multiplication in complex plane. Good. Second protagonist. Space. So we had, it's not space, it's the linear time then projected to space. So what we had before was the mechanics of of time. And now we are on Earth. And we want to do something with it. So we want to organize our ground. So this now is the Earth. It's a flat horizontal line, or a plane, or our space in spatial thinking. So you see the projections of these positions on the circle. You can see the projections. So this is what you have here. Yeah. You see the stereographic projections of the positions in time as points on your line in space. So now look at it more closely. You have an inner view, so between -1 and 1, you have the southern hemisphere, and it's going towards 0 and here, and expanding, and it's compressing, and it's expanding to this point, and that's the southern hemisphere. And if you go outside here, that the northern hemisphere is out here, and it goes from these points of identity, they're not moving, towards infinity. If you go up to the North Pole, it's infinity. Interestingly is that the infinity is on both sides. So you can't decide. There is a point of ambiguity in the infinite. The infinite on both sides is the same. So in one-dimensional lines, it's a line, a circle, unfolded, projected, and then this North Pole is on both sides of infinity of a line. If you put that, make that from a sphere and unfold it from the North Pole, unfold it, then the North Pole is infinity as a circle at the horizon infinitely, and this circle is a single point on the sphere. So we have the point of identity, we have the infinity as a conception. So infinity is both sides as a spatial line, so it's an ambiguous point. So if I now move time, you see that these sections in space, they're compressing and decompressing. That's the first thing. Then you see that these points are leaving to infinity on the left side, and they're coming back on the right side. So, or like this. That's it. So then you also see that have to take into account that these points, the projection points, are not rational. So they are not of the grid. So they are not of proportion. They are out of any proportion. They are in harmonics. They are chronological points. So, and you can see it if you, for example, calculate the 30 degrees. So this is 2 pi divided by 12, so it's 360 degrees by 12. If the I point, it's here. Then we get the cosine and sine of this angle, and then this is the formula for the projection to get this point. So we're going to take this one, and this is the point. And you have that, you see, you get an irrational number, which is this computational number. This is the symbolic expression that's precise, that's on the circle. Symbolics is able to abstract from this distinction. And now if I do it a computational number, so make it a geometry, project it, then you see it has no end, which means it's out of the reach of computability. So it's not there. which means the projection points are not real, not rational, so they're irrational, which means they are in between the grid. The grid is of rational numbers, and in between is what you can see. So which means in between these numbers and the kind of constitution, they are aliens. They are not there. They are from the time space. Projected there, they are alone. So what they're bringing with is this. So what they're carrying with them is a certain point here, in between. And what they're delivering is that they keep the angular memory of the sphere, of time. So, and you can see it here. So first I can show you that it's the same thing what we did in 2D, or something like this. So, and this is what you have here. If this is the environment, the circular environment of, so this is the angularity of a certain position in time along this axis, angularity here, and this is kept. And you can see it here. It stays a circle. So, which means that these points are, on the one hand, on a line, but they embody circularity. And this is the only things they know. They don't have connectivity. They don't have length. They just have angularity. So they have an understanding. And angularity means they are in this harmonic circle. So this is not changing. This is changing all the projections, but we had it here. We had it here. Well, so here, the interplay of these points, this is not changing. This is what they inherit, an understanding of a kind of cosmological order. This is what they incorporate. So by projection, they lose all length. All this gets crazy. So, if you do this stuff here in 2D, but this is much better here, you can look it up here or here, there, for example. You can see these distortions, especially here on the left side by rotations. You should, so you see these kind of distortions. I made a little like that here, but it takes much more time. This is distortions, and you have it with maps. Map. You have these kind of distortions. We know from everywhere. This is the stereographic projection, and you have these artifacts. You see always these kind of hyperbolic circular distortions of things, just by rotating stuff and putting, interestingly, there, and it's always cones. And then you cut the cones either with a line, so here we are with a line, and the circle, or you go to these distortions. And by rotating, you get one the circle and the other the line, and then you get to the line and to the circle. So it's always a play of line and circles, and the constituent element there is a cone, which is a line circular and stretching like this. So Therefore, what we see in on these projections, on the line, the plane, or in space, are these strange continuous distortions, the phenomenon on infinity, and the mutual flip of left or right infinity. So the crazy behavior in this projection. And it's important to notice that all these artifacts of the projections to the orthogonal, to the realm of space, to the visible, you can see are quite natural movements. It's just a movement of consistent proportions and harmonics. It's just a continuous movement within the spherical complex realm of time. You cannot see. So therefore, it's very important that you say rotations and circles we can't see. You can hear them. You can, their projections we can see, and it's very tricky to get a circle to projection and to space without distortion. But it's supernatural in time to rotate, and it's kind of irrational if you do rotations in space. And the way back. So if you do translations in space, it's beautiful. If you try to do translations on the circle in time, it's crazy. So rotations in space, in time, translations in space. And then crisscross. Now we want to go to coding details and make a recap of the whole story, but showing how to implement that in the Mathematica calculus, how to get a symbolic abstraction of that, and how to make it convenient in using it in articulating your architecture, or how CAD systems are offering it. As an architect, all you need is what we always say: translation in space and rotation, as we discussed today, in time projected to space. So you can't rotate in space, you have to do it in time and project it to space. This is translation by addition in Cartesian space, as we discussed, and it's rotation by multiplication in complex time projected to space. So this is, in my understanding, this is what I would propose, the natural thinking about architectonics. This is how things keep stable in space and time. Now it's about how to implement and to symbolize these operations in the lambda calculus and get an abstract way and to get a vocabulary for a good articulation for your architectonics. So I think this again is very important, because I think the new geometry of our time in quantum time is code and the number calculus. This is the next abstraction of projection, where you can turn the whole world in all its consistency and keep it stable and do your architectural articulations. So it's a new geometry. Therefore, now I show you how to do this with code. And again, step by step, so you get an understanding how this works. So you don't have to be able to do it by yourself, but you have to get an idea and a feeling how this is done. So you have to be able to read it in principle, not to make it actively, because this will take a few years of intensive classes. It's like learning Chinese language, writing and so on. It simply is not what you can do as an architect during your studies. But you can try to understand how the mechanics work, how the thinking works, and get familiar with it. Therefore, I'm explaining step by step. So what we have here is the definition of a stage. It's a grid. It takes a graphics and a size. It has a grid of the size, makes a unit circle, a point at the origin, and takes the graphics and puts it to the size of 256. So this is called function ST, therefore it's always capital letter, stage 01. So nothing. So we can show it, just take off, and then stage 01. We need a graphic. So okay, we need the graphics. Nothing, and 4, and then we have this. It's not too interesting. So next, now we want to go for projection of 2 points to the unit circle and then a partition of the unit circle. So projection always means you are in Cartesian space and you project points on this to time on the circle. Partition is you are on the circle and then you do partitions within the circle with angles. So it does the same, just makes 2 points. In this case, we have the origin, 0.1, 0.2, 0, 0, 2, 1, 1, 1. We normalize these points. This is a projection to the unit circle. So we take off the length, we make the length of the points 1 and keep the directions. So this is what normalization does. And the complementary function is norm, which is the length without direction. So this is the spatial part, and this is a chronological part. If I, of course, then multiply the points on the unit circle u1 with its length, then I should get the original point p1 again. So let's look. First is a semicolon, there is no output. This is the first output. These are the 2 points on the unit circle. These are the 2 lengths. And if I multiply L1 with U1, so this with this, with this, then I'm back again with 1, 1, with 2, 1, which is here and which is P1. All this works. Now a graphical illustration. Stage 1 is a function. Step 1 is not important. We will have a meet it later. So put the point here. Tooltips. Point size. Tooltips here. Point 1. Point 2. Which means I have point 1 tooltip here. Point 2 is here. 2, 1, minus 1 here. So then thickness line from origin to 0.1, 0.2. These are the lines here from origin to 1, origin 1 with the thickness of O1. And I have red points U1 and U2. These are the unit normalized things, and these are the 2 points projected to the unit circle. This is how it works. Good. Now the same thing with partitioning of the circle. So you're not in Cartesian space, you are in the circle. So which means you take an angle 1, an angle 2. You make this cosine and sine of A1, A2 to make it Cartesian in a rendering to a principally infinite resolution. So again, put it on stage, and here you are. Is it like that? Tooltip. U1, U2, here, done. Here, now we are. No tooltip. Here, we need. So with this. So this is U1, and this is U3. Okay. So these are the two principles. So it's a Cartesian, and then the other is a chronological definition of points on a unit circle, which is about rotation and directions. So, next step, now a multiplication. So we are in Cartesian setup, we can mix it as we like. So we origin, point 1, point 2, normalization. Now we put it to complex plane, so this is complex 1, complex 2, and we map these 2 points with this function to this function to get the 2 unit points. Then this is the actual rotation, C1 multiplied with C2. Put this point from complex back to real in writing. So it's not the content, it's just from the writing of a complex number to the list of 2 of the real and the imaginary part. This is U2. If we look it up, the points, the points on a unit circle, complex representation of that, the rotated point C3, and here the U3 and the unit circle. If we stage that, this is what we had before. This is inherited from our drawing up, and we said this was step 1, the first rendering on that. So then we add point 1 red on the point on the unit circle, and we see we make a red line from the origin to this rotated point on the unit circle. If we look it up, here we are. So we have inherited this setup with these 2 points. Then we add this rotation to this rotation and end up here. Put a point here and draw a line here in red. So that's the rotation by a multiplication on complex plane. Now go with a set of points. Go a little more complex. So now instead of having 2 points, we have 5 points. These are the 2 points we know. We add 3 more points, P3 to P5. Now we map all these points to the function normalized to get the points on the unit circle. We get the length of the points by mapping the points to the norm function. So we map all these points from the unit circle to the complex plane, mapping to this function, and we get a list of points here. So let's look it up, evaluate that. You either can, if you want to see how it works, get rid of that, evaluate that, and then you get this line as well. Or you can evaluate that and then you know this is variable. This is symbol PTSC, and then you get these 5 points. The rotated point is that I take the first of the complex and multiply it. There's a pure function. So there's a variable, pure function, there's a function without name, and map it with the points complex from 2 to -1. So it's so map this one with multiply them with all of them. So that's from 2 to -1. So it's the second to the last one. So map them to this pure function, which means step by step make it for each of these elements, put it here and do the multiplication, which then is the points complex rotated. So put this result, map that to to the Cartesian notation, and in the unit circle, and multiply that with their length. Okay, then you have this result. It looks like this. You have the original points, you have the rotation axis, and this is the resulting points. Here we are. Look at how it works. Point size, the points, these are these here, plus the rotation. Points here, these are the rotated points, the last 4 ones rotated. We need red from the length of the first point, that's the length here, 0, so this point here, to the point of P1 is red as well here, so we have double here, the black and the red one. So make that a line, the same thing, make this red line to indicate the angle. So that's the rotation. So now it's very important that we distinguish always in graphics. So what we touch in rotation and in translation is always the position, the coordinates of points, not how they are connected. So in graphics. Therefore, it's important to see that we can take the whole story and keep all the coordinates, but take another rendering. So instead of doing the points here, and this is with the so takes the points here, I take all these points. The first one is a rotation point, this one, so I don't want to see put there, and say this should be a polygon. And I take, instead of points here, yeah, this is a polygon here, and this is a rotated polygon. And it's a rotated points, and I simply can change it to another kind of rendering, another kind of how this is put into the visual. So a graphics always has the coordinates, the points in space, and then some rules about how to show it. And this is strictly orthogonal, like time and space. So, very important for our setup. So therefore, now, if we have these mechanics, we now go for the symbolization. This is, and we say it's a complex rotation of a point around another point. So normalize this point, bring it to complex plane, bring the other point to complex plane, multiply them, and bring them back to Cartesian plane. This is symbolized, these steps are symbolized with a CR. Evaluate that. Now, point 1, point 2, point 3 is CR of point 1 with normalized of PT2. And then we get a point, a rotated point. So, because we don't want to so we want to have a lot of points here, rotated by the same. We don't want to have the normalization of the rotation point inside here, not to make it for each point to rotate the same thing. So it's just to make it faster and don't make redundant stuff. So, but point 1, point 2, rotated point 3, show it. Point 1, point 2, point size 2 in black is default. Then red, the complex rotation of point 1 around a normalization of point 2, line from 1 to 2 to indicate the distance, which means I have this point, I take this 0, the reference axis, and turn it to this, and I have my point here. So it's a simple multiplication, this is what we had, and now I make a simple function for that to make it easy to use. So now, from now on I forget about complex numbers, because it's just Cartesian numbers and just say CR and done. So this is what you normally see with computing, that the thinking is hidden towards the pragmatics. And that's a dangerous thing with computing, that you always think you understand because you know how to use it. So the same with angles. So point 1, point 2, it's here. And go for stage 1, point 1, point 2, red, normalize, and here. This is the third point is complex rotation point about normalized, because this is cosinus 60, we don't need to normalize, it's already normalized. So, and then we see point this, rotated by this towards this axis, this point. Good. Now this is just to be able to work with lists of points. So now here we have a list. We rotate it around this axis. Have any this refinement. So I can have a list of points here and rotate them in total. Good. That's a symbolization. Now I want to rotate a whole graphics, whatever it is, your whole building, or just the furniture within a room. So how is this done? This, for example, is a sample code. We have a point. We have the graphic code is stage 1, as we had it from above. The point. We have the line to this point, and we have the stage. So this is a graphic code. To get this code, it's always like that. You can take this here and put it here and say I want to have the first element of it, and then you get the code. Yeah? And what if you say graphics from the last one, which is either you can have it and it's the last one, or you can take this number 1468, and then you get the graphics here. So this is the code. Now, as we put it with the keys, and that's an important technique to work with. So if you want to change code, you need a key and take things out. So in this case, for example, we want to get the points. So we want to get this black point out of the code. So the code is here, and the point is here. This is, for example, the point. So then, therefore, I make a key. I take the code, the G code, and I say A. It has to be of type point. It's here. Whatever there is, this should be A, and I want to present, if you have this point, I want to give that back. So these cases, I want to have them. If I put that, I get 2 of them. Ah, interesting. Where's the other one? There's another one. That's the origin, and it's our leg point. So these 2 points are given. So now I can say cases, G code, get the points, and don't give it as they are, but give it to me in a modified way. So which means I want to rotate these points. So take a point of complex rotation of the content of A, which means is 2, 1, as we had it, with normalized our angle. So it's normal, it's by 45 degrees in this case. So which means if I run that, I get the points rotated. So the origin is not rotated and this one is rotated. So if I have checked that, then I simply can say, instead of cases, I say, I don't want to extract it, I just want to replace it and keep it where it is. Which means I can say replace G-code points by the rotated points, coordinates rotated, and leave everything as it is and make that. And then you see this point rotated by 45 degrees. So this is how you are able to do these things in symbolic, in lambda calculus and this kind of implementation. So now another function, and I simply say what I did here with the point, I do it with all the functions, with the points, the lines, polygons, arrows, circles, discs, rectangles, graphic complex, Bezier curves, and so on. I can continue. So, which means I can put any graphics here. I put in a rotation, and I replace the point by this, a line by this, polygon, and so on. If there's a point, it's a line, and so on, and that's it. That's a function. And I make this function short as MTP-GR, mathematical MTP graphic rotation. So if I apply that to G-code, normalized 45, then I get the whole story turned. So that's the beauty of symbolization, of the lambda calculus. So do it here. Yeah, very simple. And then this is the corresponding thing for translation. So this is put everything to complex, multiply, put it back. So now I make a translation function, and I do it in, as we've seen it, in Cartesian space to make a proper translation. But I'm using the same symbolization, so I make it the same. So which means now I have a graphic translation instead of a graphic rotation. So with graphic translation I can say 0.11, for example, and let's see, this is here. If I go for my rotation, then I put it here. Yeah, I'm not sure. Okay. Now combine these things. We have a graphics. It's an opaque rectangle from -1, -1 to 1, 1. Then we have a full color, point size 2, point at the origin. So we can, if you like, we can show what it is. Graphics from this is the object. You can say frame. And you see coordinates and everything. So put that on stage and make this MTP graphic translation of this graphic object and move it by 1, 1 in Cartesian space on a stage of 4 units size. Then we have this object, we have the stage, unit circle, and the translation. So if we want to go a step further, take this thing here, the translated one, so which is here and here. Then we get another one and say this thing should be, we can put it in one line as we did it before. We want to have it in rotation. So take this, we can for example say, that's too complicated. So okay, this thing and then rotate it around 45 degrees. Make it red. If you run that, you see translation and then rotation. Yeah? Okay? Got it. Very convenient. Okay, having all this now, we finally can go to quaternions and how to implement a seamless rotation in 3D space. Transferring the whole space to time, rotating that, and putting it back to space. This is about quaternions. Hamilton method, an application. So, again, complex arithmetics in 1D. This is what we discussed. There is this multiplication rule. I multiply this axis of rotation. I multiplied by y is -1. This is how it is done, and you know it from school. This is how we implement that. We get the parameters here. We get the parameters here. This is just the location of our lists. The first one is 1, the second one is I. And then we only take the parameters to our lists. This multiplication is exactly this list here. So we have that. And if we take our quaternion multiplication one-dimensional, we have it here. Result is -71. And if we do it in the Mathematica complex number notation, we have it here. So having this, we go to 2D. The rules for the axis to make it turning and rotating. Now we don't need the circle. We need the surface of a sphere. So it's A and I and J, and like longitude and latitude. And the rules are I square equals J, J square equals 1, I, J equals 1. So this is how to bring these parameters to a sphere. Arithmetics multiplication is 1 equals that, up, and then you end up here. And this is our implementation. We are not interested in 2D, we are interested in 3D. So the rules are I, J, K. So you have a hypersphere, which is in 4 dimensions, but the hypersphere, you have the surface of the hypersphere with 3. There's no way to think about it visually. Nobody knows how to look at a 4-dimensional space. So, but we have these kind of rules. So I, J, and K. I square equals J square equals K square minus 1. I, J, you can look it up. This makes it round, whatever it means. And if you apply these rules and multiply 2 of these 3-dimensional four number systems, then you have this application, this multiplication, and these kind of calculations you have to perform on these 4-dimensional vectors to have multiplication in 4-dimensional space, on the 3-dimensional surface in a 4-dimensional space. So, okay, now remember how the arithmetics on the 2-dimensional case was. This is the 2-dimensional vector. We put it to the complex plane. We normalize it, the axis on the unit circle. Then we do this multiplication on the complex plane. The multiplication here, put it to the complex plane and get it to the Cartesian back, and then we have the rotation. Now we do the same thing with quaternions in 3-dimensional space. So we have, instead of I, we have x, y, and z. So we don't have this virtual axis which is vertical to the rotation in 2-dimensional. We have an axis, and we want to look in space into a certain direction, and we want to have this axis not distorted to the direction, but we want to look in a certain x, y, and z direction, and then we want to turn around this direction. So 2 steps. So therefore, x, y, and z. This is the axis. This is I, j, and k. And we want to normalize that, not to distort the whole thing. So it's just the direction, not the length of something. So we write it like this, and we know it from these gimbals or gizmos for navigation in your modelers. So you put your view in a certain direction, which means you look at this direction, and then you're able to turn the whole things around that. Or you have a vector perpendicular to the surface here, and then you want to turn it around there, somewhere in space. So we know it from there. So this is I, j, and k instead of x, y, and z, because in x, y, and z we are not proper in rotation. I, j, and k is proper in rotation. So now we need an angle. If there's the axis normalized, we want to have an angle around that. We call it angle, and we normalize again 45 degrees, and this is our angle. And we want to do it complex again. Therefore, we combine it. So we have I, j, and k of our axis in space. And then we take these 2 things as real and the imaginary part. So these are the parameters of the imaginary part of a complex number. This real part, it's here, and the imaginary part is here, and this is the I. So this is how we have direction and rotation in space. And if we put that into place, we have these 4 numbers. These are called quaternion. You see, that's the real part, and this is the multiplication of this parameter with this, and we are here. So now, if we go here and, for example, say we want to have a point 2, 1, 2, x, y, and z, we have the quaternion, then it's 0, x, y, and z, because now our axis is a space, x, y, and z, and we don't want to move it, we want to keep it on this axis like on the unit circle. So we want to put that, and therefore the 0 is there because it corresponds to the O and 0 and the 2 decay. So it's just on this and in this hyperspace. So just want to have a very small functionality of this hyperspace, just want to rotate things and not more. Therefore, we put it this simple. The point is O and then X, Y, and Z, which means this is not our point, this is Q1 instead of P1. So now if we can take this quaternion and multiply that with our function, then we have this. And we have the problem that it's distorted. It's something, but it's distorted. So, and what the problem is, we had it here. Let's go here. So if we rotate, look at this, rotate. So this is on the left side here, this is our rotation along the axis of the three-dimensional. So this axis here is a three-dimensional space, and this is how we want to rotate it. So the problem is that this three-dimensional space gets distorted. You see that. If I rotate it, the points are not in the proper proportion anymore. So because of that, there's a trick. So we simply say, I rotate it by a certain amount of, by a certain degree, and then I rotate it again, but in the inverse side. So which means I want a rotation, but on the other side, which means we can have it on the, it's a little complicated here, but it's explained here. So don't make it in my video. Go there and look it up. So what we have is, we invert it, we have this direction, we rotate it in a certain degree, then we go with this direction and rotate it again, which means we add the rotations and we have the scaling and the inverse scaling, which means we have a proper scaling of 1 again. That's the trick. So it's described here, and you can look it up in these interactive videos. So therefore, for example, if we want to have a circle, a rotation of 45 degrees, then our angle of rotation is half of that, and because we want to have arithmetics on numbers, we have to do it on the circle. So our quaternion is, as we thought, is then like this, a crazy number, nothing to understand. You have to understand these mechanics here. So if the inverse quaternion is that we keep the rational number, and the axis, we simply say it's just the other one. So it's in this, it's like this, so it's minus, 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 that's inverse. So we have the inverse. So, and what we do now is get this quaternion multiplied with our point, multiplied at QM3, and multiply that with our inverse quaternion, having half the, so which means I have half times the rotation, 2 times, and I have the scaling in this direction and scaling back to 1. So if we do that, we have a 0 here, and we keep everything, all our information within the space. There's no distortion. So that's good, and it's just this game. You should not try to understand it visually. Yeah, I'm pretty sure that's the way how to do it. This is a compilation of what we did. So we have the axis, we have a rotation, we have a quaternion, inverse. This is our point here, and then the rotated point is this, what here, and here we are. Now we have graphical validation of the result. What is this? No. Okay, make a sphere. Basically, infinite line, now infinite plane. So I think this is enough. So to get some orientation. So you see how complicated these things get. So we have, and again, it's about trusting what is there. So we have the axis, it's here. That's a red infinite line from 00 to this axis. So we're looking in this direction or in this doesn't matter in this case. So that's our axis, that's a red one, red line. Then we have a black point, this is the original point, and then we have the rotated point. So we always take 2, 3, and 4, so the x, y, and z coordinate, because this is always 0. So we can skip it. So it's the same here. So we have black is the original point, red is the rotated point. So and it's a kind of rotation, so we have changed the coordinates. So now, and we did it by 45 degrees. So now if we put this, so that we are in line of the axis, we see a 45-degree rotation. Put that to 60. Render that, and we see a 60. A 90, just to prove it, or to validate it a little. And here we are. Yeah? That's a kind of validating of results, of crazy numbers. So, again, symbolize it in a, we say MTP complex rotation. We say x, y, ax, axis, and then rotation. We keep that as a pure function. Make this rotation. So, which means rotation about 1, 1, 1 is our axis, this kind of degree of this point. So, and here we already cut, with the result, we already cut the first, the real part, and here we are. So it's directly a rotation in three-dimensional space around the axis with an angle. So, to show that this is actually working, we have this polyhedron data. So this is here. This is an object like this from the polyhedron data database, an octahedron. This is the actual data. It's a graphic complex. We have the number, we have the coordinates, and we have the connectivity of these things as polygons. We have to change these numbers, so which means the points, source of 1, source of 1, so source is this. The first one, we can check. Source 1, these are just the points, which means I take this complex rotation around 90 degrees around this axis, as we discussed here, then map all the points we have to the rotated points, get it here. So, oops. Points at this. Points are these are the points, and these are the rotated points. So these are precise. They are described in on circles and an irrational plane. These are computed numbers to make that readable, more readable. But we have the problem with the with precision. These are 100% precise. The symbolization of numbers and algebra makes it precise in the irrational domain. These are only infinitesimal correct to a certain amount of resolution. So you can skip it. If I put it to n, it's down here. And show it here. These are the actual formulas. Good. Now we take our stuff from here to here and say we want to have the sphere, we have a plane, we have the infinite line of the axis as we had it before, and then we make a graphic complex of the points with source of 2. If we look at source of 2, these are the polygons. This is the topology of our graphics complex. So, and then we do the same and just replace the points, lighting, neutral, blood, and so on, and here we are. So if we put this, we have the opacity, unfortunately. So if we put this with the 90 degree of rotation of any object. So how to symbolize that with full graphics? We had this example in the 2D case. This is a shortcut how to show that this is working with the quaternions. You see more on that on this interactive visualization. We had it several times. Go there and look at it, but be careful. It's not a visual problem. I think with this lambda calculus, much more adequate. So with programming and with coding, it's much more adequate to learn how this is about. So therefore, I have been very extensive in this aspect. Last chapter, showing that how it works with unity. We had it in the last lecture. Then previous lecture, it was on unity. We have to start unity links. We open a new project. This always takes time, it's super heavy. But come on. Recording takes its time as well. Normally it's double. Good. Here we are. We have a connection. So we take a polyhedron, dodecahedron. We create, we name it OBG. We create OBG with this name, unity object. Name it like that, and we don't need this. And we see here's our dodecahedron. It's called like this, and it has its component, transforming component here, and you see all this is proper. To get the components, take off UTY, transforming component, and ask for the rotation, and you get quaternion. Yeah, these four numbers: real part and then the axis, and they are crazily interlinked to make it stable and in scaling and not distorting. Keep it round. So now we want to change it. So we make our axis as we did it before. We want to rotate around the axis X, Y, and Z with an angle of 45 degrees. This is our angle. This angle is unity needs computer numbers. You can't have these symbolic descriptions of irrational things with like square roots of something or sine cone. So they can't resolve it. So therefore, cosine of half, we learned it. Why? Half sine, half cosine. Therefore, the quaternion is this. So crazy numbers. So we set the property of our transformer, local rotation, which was this, to our quaternion. So make this again to be sure and make that. And we should have it here, 45 degrees around minus x, which is a strange setup. So it's a strange setup in Unity. They have z, y, x, and certain directions, so it's not the big problem. So some other conventions how to read that, and that's it. You see how to control things in space and address it to a 3D modeler. So that's my talk. You see, it was extensive. It was very exhausting to prepare that. It took me a long time. It's not finished, it's not slick, but I think it's good like that. So, and this is, I think, the approach to how to deal with it. And you imagine it's more about meditation, about space and time, and being an architect orchestrating that and getting a certain mechanics for that, than proper mechanics or coding and this kind of intuition and getting visual and so on. It's just meditation of what is space and time, what the hell numbers are, what multiplication in contrast to additions are. And these are the questions and nothing else. So, and I think as architects we should concentrate on that. Not necessarily on coding. Coding helps to think properly and to evaluate things, your thinkings, but it's definitely not about the intuition of your eyes, because it's just half of the story. Your senses and your body is in a different realm than the visual one, which is just cutting things. Okay, that's it. Hope you enjoyed it, and it was not too much, but I don't know a simpler and faster way. Thank you for watching, and see you.